Okay, so we are continuing on with chemistry, and now we're gonna. I guess if we were to kind of review the progress that we've done. First, we started off talking about atoms and the way they behave and their electrons and how they gain and they lose and all that good stuff. Then we put atoms together, and that brought us to compounds, how they can come together in certain combinations to form various types of compounds, ionic versus covalent. I don't believe I'm giving anything away there, ionic versus molecular. And now we're ready to put the chemicals together, the compounds together, and talk about chemical reactions, all right? And we're actually nearing the end of this long procedure of our chemistry unit. We're going to talk about chemical reactions and how we write them down over the next couple of days. So if you take a look over there, we've got chemical reactions. Tomorrow we're going to talk about something called the law of conservation of mass, and I'm going to demonstrate another little experiment for you, and then we will start into talking about balancing chemical equations. We'll take another day on Wednesday to balance chemical equations, and then we will get into talking about specific types of chemical reactions. Chemical reactions can fall into various categories, and they help us understand how to maybe how to complete or balance a chemical reaction. So that's what we will be doing next. Once we're done that, into next week, we'll be talking about acids and bases, very special chemicals that we encounter a lot in everyday life. So we're going to talk a little bit about that. And that actually then brings us to the end of the chapter. So I'm not exactly sure how many weeks ahead we're talking. It's obviously not this week and not next week, but maybe into the third week from now, we'll be getting ready for a big unit test, all right? And then that would be everything on chemistry when we get to that point. So there's a little bit of a heads up. Okay, so very straightforward business here. I do want you to write down, now what was the title on that previous slide? Understanding chemical reactions. So I don't think we need to necessarily write down chemical reaction. You already have that as the title. So we can write down the bullets here. Talking about reactants versus products. This is very much review. Again, I haven't done the grade 9 in quite some time, but I'm pretty sure you've talked about chemical reactions, and I'm pretty sure you've talked about reactants versus products. And so if you're finding this to be extremely redundant, then that's great. That means you remember what we told you last year, which is okay. Now, when we get to some of these next slides, hold off a little bit before we start writing like crazy. You guys are good. You start writing right away, which is excellent. Like I said, this is very much review. Let's be critical about what we're writing. If we remember it and it's very obvious, then maybe it's not necessarily worth writing down completely, right? Sometimes we write too much down and we get too much information on a page. Again, those of you who are finished writing the quiz, you can always take a look online for the PowerPoint. Representing chemical reactions, I'm going to just, I don't even know why I have the animation. I do want everything written down on this page, though. Wait a minute, I need one more product here. There we go. So no matter what type of equation you're writing down, whether it's a word equation or sometimes some teachers call them skeleton equations before you balance them, or chemical equations, and we've got balanced chemical equations. As you continue on in grade 11, I'm going to teach you something called ionic equations and total ionic equations and net ionic equations. There's all kinds of really different subforms of this. It's always the same: reactants on the left, an arrow in the middle, and products on the right. I very often have students in a hurry put an equal sign in the middle there. I'm really not too critical when you're young chemists, but in the end it really is supposed to be an arrow. It's representing that transformation of the reactants to the products. The simplest type of equation that you can encounter is a word equation. It's simply just, you know, writing the names, the chemical names that we practiced in the reaction. It has nothing to do with numbers of atoms and balancing anything. It has nothing to do with that. It's just simply a statement of what we used as the reactants and a statement of what is produced at the end of the reaction. All right? So there's nothing really earth-shattering in a word equation. It's a very simple representation. But we do need to use proper terminology when describing the chemicals. We need to use their proper names so that we know how to turn that into a chemical reaction that we can balance. So that's where we're heading eventually. That's what we want to be able to do. You've seen word equations before? Grade 9? Yes? All right. Did you do any balancing? Did you balance any chemical reactions? No, depends on who your teacher was. All right, that's fine, that's good. If I say balancing chemical reactions, do you kind of understand what I'm talking about? No? That's fine. I'll explain it in a day or two. Okay, so don't necessarily write down that second example. It seems a little silly. So let's just write down the bullets here, or the definitions. Yeah, right there, thank you. So again, I've got a second reaction here, but we already have hydrogen and plus oxygen to get water. This is a little more complicated. Propane gas that you might have in your tank for your barbecue, plus oxygen to produce carbon dioxide and water. Not a big deal. The reactants on the left, the chemical that is present at the start and is used up during the reaction. We state here that it's used up, but sometimes when you have more than one reactant, sometimes one of the reactants is used up first, and there's some extra of the other. The reaction will come to an end as soon as that first one is used up. In the reaction of propane and oxygen, if we're talking about a propane tank, the propane is going to be used up first. Where does the oxygen supply come from for your barbecue? Where does the oxygen supply come from? You got a propane tank. Where does the oxygen come from? Yep, the air. So the oxygen very rarely runs out in the air. That would be cataclysmic. Oh, I've barbecued too much. I've used up all the oxygen. No? Not funny? Monday morning? Monday afternoon? After the quiz? Nobody's laughing. It's just a general Monday situation. Okay. So we say that they're used up, but if you've got more than one, typically only one is used up, and then the reaction stops. Product, the chemical that is produced during the reaction, that's pretty self-explanatory. And the purpose of the arrow indicates the direction of the chemical reaction. And you might think, doesn't reactants always become products? Well, in your world, the answer is yes. When you get to grade 11 and grade 12, I'm going to teach you about something called an equilibrium reaction. There are even some kinds of reactions that we say are reversible. So there are some reactions that can go both directions. In this case, this is what's called a combustion reaction. It doesn't run in both directions. If you're going to burn some propane, it all burns. You've never ever seen carbon dioxide bumping into some water and turning into propane. That doesn't happen. This is not one of those reversible reactions. But there are reversible reactions that exist in nature, and so the arrow is indicating which way we're heading. For our purposes, always heading to products. We sometimes read it as yields, produces, forms. So just like I was trying to teach you the language of telling me how to draw a Lewis structure with the terms single bond, double bond, you would describe this as being propane plus oxygen to produce carbon dioxide and water, or yields carbon dioxide and water. That's how you would read it. Okay? All right? Again, just a little discussion on the arrow itself. Again, to you guys, the arrow is almost like magic in that we start with reactants, some kind of magic happens, and we have products. In reality, there is something that is taking place during the arrow, all right? There are chemicals that are that are breaking bonds and things reorganizing themselves until they get to the point where we have product molecules. And in grade 12, we'll talk all about what happens during the arrow. It seems like magic, but it isn't. There's things going on that we can understand as chemists. For now, you can just say that it produced. Okay? All righty. So let's just do a couple of examples here. Let's do A. I don't want to bother with B because because I've also got a C and a D, and again, I didn't put these together. Let's just do two of them. Let's just do A and D. So please just write down A, and we'll work on this one together. And then we'll do the D on the next page. You can call it B, you can call it whatever you want to call it. But I think 4 examples is a little overkill. We got any more quizzes out there? All right, which is good because now we're going to be doing some naming, which, I don't know whether these were on the quiz or not, but they might have been. So it's a good thing. Everybody's done. What is that first chemical called? What are we calling that first one? Again, it's Monday, so I'm not going to wait for all these hands. Marissa. Sodium sulfate. Sodium sulfate. I'm just writing it underneath because I'm afraid I'm going to run out of some room here in a moment. And with a plus, what's that second one called? Yep. Lithium chloride. Go ahead. If you don't have to wait for me. If you're figuring this out, go ahead. Go ahead. Lithium chloride reacts to form. That's where my arrow goes. Name of our products here. I'll take one. Either or. Doesn't matter to me. Yep, James. Sodium chloride. Sodium chloride. And our final product. Yep. Lithium sulfate. Lithium sulfate. Right? Okay. Again, I think 4 examples is a little overkill. So go ahead and actually, no, I'll work with D with you. If you get the idea, that's great. You can do it. We're doing D. We're just going to do D. Yep. Yep. That's exactly true. We call that particular type of reaction, we call that a double displacement reaction. We're going to be talking about that a little later on. In that particular type of reaction, a couple of the metals just traded positions. That's exactly correct. Yeah, and that's a very specific type of reaction. We're going to do an experiment on it, et cetera, et cetera. So that's a good observation. You bet. There's all kinds of different ways in which these chemicals can do things, and that's what we're going to get to near the end of the week. That's correct. Good observation. What is this first stuff called here? Yep, Marissa. Barium carbonate. Barium carbonate. Now notice it says it just reacts when heated. In this case, we have no other reactants. This chemical is there, it's being heated, it has all kinds of energy being put into it, and it then just produces a substance. This is a type of reaction as well that we'll be seeing in the future. Again, to produce, I'm just going to finish it off, barium oxide, and what's that last one called? Yep, carbon dioxide. It's molecular, so a slightly different name. Carbon dioxide. And a little notation. If you are heating something, we sometimes put a little symbol over top. We put a little triangle there, and that represents to heat something. All right? So that sometimes is used to represent heating. Other things that can be placed over the arrow, are sometimes things called a catalyst. Have you ever heard that term before? A catalyst? Does anybody know what a catalyst does? What does a catalyst do? Any ideas? They don't chase cows around or anything like that, like in a pasture or something. A catalyst? No, it's not funny at all. Again, not funny at all. It's all right. It's okay. A catalyst is a chemical that is added to a reaction that makes the reaction go faster. All right, and it doesn't get used up in the reaction itself. It's just a chemical that makes a reaction go faster. And if you have a catalyst, we sometimes also place it over top of the arrow because it doesn't actually get consumed or produced. It just helps the reaction go. We won't bother writing that one down. Okay, let's now talk a little bit about a chemical equation. And the chemical equation simply replaces the names with their chemical formula. Now, this is not what we call a balanced chemical equation. Again, I'll inform you tomorrow on what that means and why that is. So notice in our word equation, we didn't say hydrogen gas, but that's okay. We need to realize that if it says hydrogen in a reaction, that is one of our Hofbrinkel gases, and therefore we write it down as H2. It also didn't say oxygen gas, but that's okay. We know again it's one of our Hofbrinkel gases, and therefore we write it as O2. Again, the arrow is the standard arrow, and that produces water, H2O. All right? So be aware of that. If it says chlorine, you need Cl2, or bromine, Br2, or iodine, I2. All right? Okay. You guys are easy to talk to. Just sitting there writing things down. Perfect. Some important little notations that go along with this. And again, if you did the reading, then you've already got this. That's great. And it's review. If you didn't, well, then you're getting away with it because I'm telling you all the important stuff that was in there. Sometimes we use subscripts that go along with the chemicals to indicate their physical state. So sometimes in brackets we'll put a little S. It represents that it is a solid. L representing that it's a liquid. I've often seen the L as a script, just so that it's not confused with something like an I or a 1, right? Because that almost looks a little bit like brackets 1. So I've often seen the L written as a script. In textbooks, it's not, because it's more convenient. You just put the font L, whatever it is. It's not a big deal which it is. G is gas, and AQ stands for aqueous. It means to be dissolved. So we talked about dissolving on Friday. So if a substance is dissolved in water, like the sodium chloride when we put it in there, or even the sucrose or the dextrose, we would then put AQ to represent that it's in a solution. Right? So sodium chloride, NaClS, you need to think of a little container with a white solid in it, right? Like salt. But NaCl aqueous, you're thinking of a transparent, colorless liquid that if you tasted it, it would be salty, right? So the symbol represents what physical state it's in. We're good to go? Don't see any pencils wiggling around anymore. So write a chemical equation for, again, what have we got here? We've got the same stuff. What's going on here? We've got the formula here. That's good. Reactor oxygen. I don't want to do the oxygen one. Let's do these examples. Let's do this example. Awesome. Right there. Just put EG. More examples, whatever you want to write there. EG. I should have actually, I'm going to try to squeeze an answer in between all those spaces because I am recording it, and I guess if you want to go back and look at the answers, I got to put them somewhere. I should have maybe spaced them out a little bit. You can write down all of them if you want, or we can do one at a time. It doesn't matter to me. But I'm going to try to squeeze the answers into here so that if you want to go back and look at the video, you can have a look. So here we have some carbon, and it's burning in some oxygen. It's charcoal, all right? So you can imagine that as being that solid black stuff that you can use in a barbecue instead of propane, right? You could use briquettes, charcoal, and it's producing some carbon dioxide. So in terms of the word equation, I've already said all the terms, so I'm going to just write it out. This would simply be carbon. All right, carbon plus oxygen again, in this case, to produce carbon dioxide. All right, very straightforward. Yep. Yeah, you could. That'd be great. That'd be a great thing to do because we definitely have to heat that in order to make it happen. If you didn't do it, I wouldn't be that concerned. It didn't say, it does say that it's burning, so that's good. It doesn't imply that it's necessarily being heated, but that does make sense. So if you got it, that's great. Write the states for each of the substances. Carbon, what state is carbon in this case? Yep, solid. The oxygen, what state is our oxygen in? Yep. Gas. Maybe I shouldn't use arrows here, but I think you get the idea. Here, I'll make the arrow look a little different. I'll give it a double, like kind of thing there. That's gas. And the carbon dioxide. And what is it? Yep, Sammy? It's a gas as well. Gas. All right. What evidence suggests a chemical reaction took place? What do you think? What do you think, Shane? Sorry? It's burning, so it's giving off heat, right? Probably giving off light. Yep. Yeah, the carbon started off as a solid, and it's definitely going to be, it's definitely not going to be that case in the end. So multiple things, changing of a solid to a new gas, light, heat, etc., etc. I'm just going to put that in point form. Light, that's terrible. I don't know what happened there. Light, heat, all right. Change of state, Got to be careful with that one because changing state is a physical change, but it's a solid disappearing into the gaseous state. All right, so that's a different thing. Okay, what would you expect to see when this reaction is completed? Something that we could observe from the experiment. So in the end, what would we see? Yep. Not necessarily, actually. Smoke is produced when something like a piece of wood is burning, and inside wood there's more than just carbon. There's all kinds of different minerals that the tree has taken up. Things like potassium and other light metals. And if wood doesn't burn hot enough, then you're getting little particulates coming off of the wood. But if you burn it properly, like charcoal, and you burn it with lots of oxygen, you actually shouldn't get smoke because it should be burning very cleanly. So in this case, you may not see smoke. What would you see when the reaction is done? And it's all based on the states. It's all based on the states. Yep. You should see nothing. Excellent. You should see that that solid carbon is now gone, and everything else has been, turned into gas, and whether it goes into the air, it depends on where we're burning it, if it's in a container or not. But you should see nothing, because everything has been turned to the gaseous state. So what would you expect to see? Nothing. All right? The products are gases, right? And why is that? Because CO2 is a gas. All right? Again, I'm doing everything kind of point form here, and you can in your note, but when I ask for a test, I'm going to want a little more detail, but I think you guys get the idea for that. Okay, let's do one more example. Yeah, one more example, and then we're done for the day, and I'll let you work on the homework maybe if you didn't get a chance to finish it, along with these extra 2 questions. Yep, no problem. So here we've got more of just a statement, a description of the chemical reaction itself. We could go to the word equation and then the chemical equation, but I think we could do it in one shot. I think we could go straight to the chemical equation. So without, we don't want to write down a word equation. It doesn't state it. So let's see if we can go straight to the chemical equation. But just from the words, what are my reactants in this particular statement here? What are the chemicals I'm starting with? Which means I've got to figure out the formulas for them so I can put them on the left. What are the reactants in this reaction? What are the reactants in this reaction? What are we starting with? What do you think? Yeah, excellent. Zinc and copper 2 sulfate. How did you figure that they were the reactants? That means to produce, and those guys coming after it are going to be the products. Excellent, very good. So the word yields or produces is going to indicate what our products are, so that's got to be that. Do you have any formulas? You got the formula for zinc? Zn, and let's put the subscripts to indicate their states. Yep, S, very good. SO4, did I need to cross over anything there? Copper, in this case, copper is 2, what's sulfate? Sorry? Is sulfate 1, what is sulfate? Sulfate is 2, because its charge is -2, right? The charge. So 2 and 2. Okay, and are we going to describe its state? AQ. Excellent. To produce, or yields, a copper precipitate. Not right now, man. I'm busy. Right in the middle.
That's my phone.
Nicely done. Good job.
You want hockey, right?
I do.
Sure.
Makes good sense. All right. What are my products? A copper precipitate. Yep. Yep. Cu solid. And zinc sulfate. Formula for zinc sulfate. Yep. ZnSO4, because what's the charge on zinc? We do need to know that, because charge on zinc is 2, and what's it on sulfate? 2, so yeah, we're good. And what letters get there to indicate its state? What am I putting there? AQ? AQ. Excellent. Very good. Write the state of each substance. We did it. What's the name of the solid produced? I think it's pretty obvious. Copper. Copper. What they're testing out for you to know is that the precipitate is a solid. It's forming a solid as it comes out of solution. And the aqueous means that this is still dissolved, so we wouldn't see it. There's nothing to see there. It would be all transparent, and zinc, I think, is colorless, but I'm not sure. I'd have to take a look. What is the name of the reactant solution? What we're testing here is whether you understand what these subscript means. The reactant solution. What's it called? Mackenzie? Copper 2 sulfate. It's copper 2 sulfate. Copper 2 sulfate. All right? Okay. So last day, which was at the very beginning of the PowerPoint there, I think we had 227. I think it was 1 to 5, right? And here you've got 7 and 8. It's not very much. We're down to a little less than 20 minutes. You might be done in about 5, but I don't want to talk about the law of conservation of mass quite yet. We'll deal with that tomorrow. Okay? Everybody clear? All right. I'm going to stop the recording here.